from Trinity College in Dublin, who is going to explain us his joint work with Vladimir Dochenko, tangent complexes and the Diamond Lemma, homotopical methods for term rewriting. Go ahead, Pedro.
Thank you very much, Ima. It's a pleasure to be back in a conference, at least virtually. It's been a pleasure to enjoy the other talks. I hope that today I'll be able to mention some things, some new things.
Well, you will be back to Barcelona really soon, and also back to real talks.
Yeah, I think
for some time.
Yeah. But what I want to tell you about today is a relatively recent paper we finished with Vladimir, where we explain how to sort of build a bridge between not a new one or perhaps a little one. There are others that exist between perhaps what has been mentioned what has been mentioned many times in other talks, which are ideas of homotopy theory and term rewriting. Now, I believe that some term rewriting may have been mentioned implicitly, and I would like to mention that later, but let me begin with the first slide. So basically, this talk, as I was mentioning, is our goal is to sort of pave sort of the road between certain effective and combinatorial methods that exist in writing theory, and then a lot of interesting formalism in homotopical algebra. And when I say continue to pave the road, I'm thinking of this analogy that I think Vladimir once told me, where you have like these two little, very not little but nice cities, one away from each other, and they have beautiful roads. And then once you start moving outside the two cities, the roads start to be less taken care of. And then, you know, if you want to get from one to the other, you need to make an effort. So I think that at least in that spirit, this talk is aiming at taking care of the roads in between the nice cities that we already know. And so the first one is the first city, perhaps, is term rewriting theory. And if you have worked, or if you work with term rewriting theory, such as Grosvenor bases, rewriting systems, overlappings, ambiguities, then this talk will tell you how you can use methods coming from homotopical algebra to gain intuition as to where exactly the Diamond Lemma comes from. So I'm assuming that you know what the Diamond Lemma is if you come from writing theory, and if you don't, and if you enjoy homotopical algebra and all of its powerful tools, then what I will give you today is a way to discover an effective method of computing things and finding information about algebras, operads, shuffle operads, non-symmetric operads, perhaps, using a perhaps technical test that's called the Diamond Lemma. But well, ideally it will be clear as I explain everything. So I don't have a lot of slides, so I would like to give you as much detail as on each slide. So let me tell you a bit about the organization. So first, I want to give credit where credit is due and tell you a bit about what other people have done before us, some bridges or some paved roads that have been created. Second, I want to tell those that are not perhaps terribly familiar with the term writing theory and Diamond Lemma what everything is about. So a bit about the whole setup of the term writing theory. And perhaps if you already know what term writing theory is, you can relax and drink a coffee while I do that. In the third part, I want to move on closer to homotopy theory and talk about perturbation and deformation theory of differential graded algebra. So if you know about homotopical methods, here you can relax. And if you don't, here is where I'll tell you something new. And finally, the sort of common denominator will appear with tangent complexes and the Marek-Cartan equation. So the Marek-Cartan equation surely has been mentioned just some minutes ago. Tangent complexes have been mentioned, for example, in Jose's talk when he was talking about derivations. But well, here, hopefully I'll give just an introduction in terms of associative algebra. So very, very down to earth. And finally, once everything is set up, I'll tell you about the main results that we have obtained. But the picture should start drawing itself as I start talking. So let me tell you about the bridges. There's a general principle if you have perhaps computed resolutions, if you have done computations with algebras, polynomial algebras, that a bit of the information of the algebra comes from what's called a unit algebra. Now, if you don't know what the unit algebra is, you can think of getting information of a topological space from its cohomology algebra. So you lose some information when you pass to the unit algebra, but you get information. You replace the difficult object by an a priori simpler one, and you obtain information. Now the question is, how do we compute it? So in the same um, in the same case where you would be given a topological spaces and you say, oh, how do I compute it? Well, if you have a combinatorial description of your topological space, you have a priori an algorithm to compute its cohomology. This happens in a similar way for algebras, but you need to compute projective resolution. So the work, for example, of Greenapple and Zakaria in the decade of the 80s showed how to compute resolutions of simple modules, so the building blocks of the category for monomial algebras. Now, monomial algebras are the ones that I'll be mostly interested in, so let me tell you what they are. They're just algebras presented by some relations that are monomials, as the name says. So they are usually, in this paper, they're called zero relation algebras. Then there was kind of a series of works after that. Anik, quite immediately after this work, figured out how to extend the work for monomial algebras for a larger class of algebras, generically, quote unquote, any algebra, in the sense of, you know, if you present it by a nice set of equations and relations. Barcel realized how to extend the work of Anik to go from modules to bimodules. So Anik did it for modules, Barcel did it for bimodules, and then Sergio Choi and Andrea Solotar did it for not for Grobner bases, but for rewriting systems. Now, these two things are very similar, but they are slightly, there's a nuisance, no, not a nuisance, sorry, I mean a caveat between going from one to each other. So in the thesis of Sergio Choi, he explained it how to do it for a rewriting system. So a rewriting system you can think of as a presentation of the algebra that is, it's like giving an orientation to your topological space. Sometimes you produce a topological space, you glue some things, but a writing system sort of gives you a bit more so to compute with it. And Skolberg, in 2005, he published a very nice paper where he explains how to take this bit, so it's cohomology, and how to take the algebra itself and produce a spectral sequence. So here, perhaps, this is a bit more technical, to compute the Hochschild cohomology of A. Now, perhaps I think I can annotate. So let me draw another parallel. So what he said is that if you take the cohomology algebra of your space, and if you take the sort of singular cochains of your space, you can do something to it, and this will converge to the homology of the loop space. Something like that is what he said. So if you know some algebraic topology, this shouldn't surprise you too much, that there's a spectral sequence going from the cohomology of something to something more complicated. I'm not being precise. This is sort of hand wavy, but I hope it helps understand what exactly Emil was aiming at there. Now, on a second sort of line of ideas, we can take a presentation of an algebra and already from it, without doing a lot of difficult machinery, we can obtain information out of it. So, for example, a work of Ufnarovsky in the decade of the 80s too assigns to an algebra a graph. It's called now the Ufnarovsky graph. And if that presentation is nice, meaning it's a Grobner basis, I can explain what that is later, then the behavior of paths on the graph, which is directed, coincides exactly with the behavior of how the algebra grows. So just to, I don't think I want to give you a concrete example because it will take me a bit. But basically what he showed is that the growth of the graded bit of the algebra, so the growths of these things, is in bijection with the number of paths or directed paths of length potentially n+1. Here there's a shift that I wouldn't remember now, but he definitely gave a very concise description. And one of the very interesting things about this result is that in the case of graphs, there's a dichotomy. The growth of paths in a graph is either polynomial or exponential. And this, I would say that was sought after for algebras, but I believe that at least it was recovered here if it was already known, and if not, it's something that was proven with this very elegant combinatorial procedure. Now here, perhaps I'm going to mix two of the ideas that I just mentioned in unpublished work of Joe Chuang and Alistair King, and later in a paper of mine. What I did and they did was use Grosvenor basis plus a bit more of combinatorics to find resolution. So if you want to think about it in terms of homotopical algebra, there's a way to find cofibrant replacements of objects through the combinatorics of the defining relations of the algebra. And the procedure is very concrete, it's algorithmic, and it gives an answer sort of like that. The way that the answer is obtained is a bit more difficult, but interestingly enough, it uses an algebraic version of the discrete Morse theory of formants. So there's a way to start with a big model and collapse some cells according to the relations of your algebra, and that gives you sort of the smallest model of your algebra. And finally, there's a recent paper of Green-Healy and Siebel-Schroll that proves that whenever we choose nice presentations of algebras, we can construct affine algebraic varieties, and that the leading terms of the algebra actually control certain generic properties of the points of the variety. So, for example, the global dimension, the Cartan matrix, if you know what this is, the property of being n cosul, property of being, well, cosul, the Hilbert series. And this paper, I think it's wonderful in particular because it makes very concrete sort of a motto that we have, which is precisely this, that how can an algebra be understood in terms of leading terms? And this paper gives a very satisfactory answer to it. Perhaps since I'm mentioning the work of Siebel-Schroll, I could remind everyone to sign the petition that has been distributed in the webpage. I think everyone that has not signed it should definitely sign it. And let me now tell you precisely all the terms that I've been talking about, so that we give you a short introduction to what term rewriting theory is. For those that enjoy more homotopical flavored things, that will come perhaps in a bit. So I think there's a question. Oh, there's a petition for regarding some executive decisions from Leicester, sorry. I think the link is in the webpage of the conference, correct, Emma?
Don't worry, it's there, yeah.
Yeah, I could send you an email later.
Thank you. That's good enough.
Okay, sure. So let me formalize a bit all of what I've been telling you about. So our general setup will be that of associative algebras, and associative algebras are presented luckily by monoids, meaning if I want to define what a free algebra is over a field, I can define monoids and linearize them. And this will actually, it sounds innocent, but it will be important later, very, very at the end of the talk. So what I will do is I will fix an alphabet, which will be my basis. I will take the free monoid on that alphabet, and I will form the tensor algebra. Perhaps here this should have brackets, but well, this is just the K-span of monomials. And you may have heard of the so-called word problem, that whenever, well, we have some relations between words here, or actually what I mean to say is monomials in the words of X, one can ask, when are two words that you give me equivalent? And now, in the context, for example, of group theory, this problem is extremely complicated. There's a whole part of group theory that is dedicated to the solution of that, or the two statements that say that it cannot be solved in very concrete terms. Because we're dealing with monoids and we're not dealing with groups, things are a bit nicer. So here we do have a satisfactory solution. So very well. So the general setup is that we will package our datum, meaning our alphabet and our relations actually into a function, into a triple that's called a rewriting system. So a writing system is just a triple where I have chosen my alphabet, and I think I tried to use the spotlighting the other day, but it didn't work for me. Yeah, so it's not working, so I'll use just the pen. So what we will do is we will choose an alphabet. We will choose some monomials, which I use the letter W for words, and then we will use a function that will take our words and will give us what we like to think as remaining terms. So let me give you an example here, as if I was on a board. Perhaps we can consider the word XY in the alphabet X, Y. So this is a single word. So this is a set of words, and the function f sends XY to YX. Now, this could have been YX plus Y squared, perhaps, or it could have been YX minus X squared. But for our purposes, this is a fairly good example. So this function is defining for us certain rewriting rules. It's telling us that certain words that we have chosen in our free monoid can actually be rewritten, and I'm using Artin's here arrow, into other words. That's one point of view, which is very helpful. And the second point of view is that, well, just simply taking the graph of this function, we are defining our relations in our tensor algebra. So in the example I just gave, if I take this, I'll just get, well, XY minus YX. And so I'm giving you a presentation of the free commutative algebra on two generators, right? So precisely what I was saying just now is that whenever we have that situation of a writing system, which has all the information that we need, words, alphabet words and rewriting rules, we can form an algebra, which I will consistently denote by A sigma throughout the talk. So in the case that I was writing here, A sigma will just be the polynomial algebra in two generators. Okay, and a basic question that arises whenever we're studying an algebraic object in general, but in particular an algebra or an operand or a prop or something like that, is, well, how can we give a k-linear basis of it? It sounds like a really silly question, but if we want to actually start computing with the object, we better have a k-linear basis of it, and not any basis, but rather a basis that that is actually useful for us. Okay, so that's the question, and the answer will come soon. So what is the first thing that we do? Well, we think of the most essential thing that we can do is that whenever we have elements in the tensor algebra, we can rewrite them according to our rule. So whenever we have an occurrence of our word inside a monomial, we rewrite it. And basically a basic reduction is one choice of occurrence of one word in one monomial. And all of them give us the most generic way of rewriting inside of our algebra. And our first attempt at finding a basis is defining things that are fixed, that are sort of fixed points of basic reductions. So these are the irreducible things. Something is irreducible if you cannot rewrite it. And a normal form, just a linear combination of irreducible monomials. So our goal actually is not only finding any k-linear basis, but finding a basis of normal forms. But there is a problem that, well, whenever we look at this algebra here, it receives a map from irreducible from normal forms, but that may not be surjective and it may not be injective. So let me explain you how both surjectivity and injectivity might fail. So the way surjectivity may fail is that whenever I choose something and I try to reduce it until it's irreducible, it won't finish. So termination will fail. So if in every situation that we consider an infinite sequence of acid reductions, things stop, we will say that the system is terminating. And surjectivity is not as delicate as injectivity. We'll see about injectivity later. So usually we assume that our systems are terminating, and I'll explain now how to do that. But what I have sort of stated here is that, well, a system is terminating when this map is a surjection, and we want a bijection, right? But one way to make sure that things terminate is to have an order, and if that order is a well order, well, we know it finishes. So the idea, the general idea of rewriting theory, is to take our words, take our free monoid, and define a partial order in it, which respects the product, which is compatible with the rewriting system, meaning that whenever I rewrite something into something smaller, then when I rewrite something, let's say W into f of W, everything that appears here is smaller. So we're sort of making things smaller and smaller and smaller. And well, the third condition is that this is Noetherian. It's a well order, so the descending chain condition holds, and we know that even if we rewrite and write, at some point we will reach a fixed point. And this is a fact that I can tell you just because it's useful, but basically termination happens precisely when this holds, when there's a partial order with this. And I won't prove it. I wouldn't say I can explain to you the proof in detail now, and I don't think it's necessary. But just to give you an example, similar perhaps to the other, if we take three words and we declare that z squared rewrites to xy, then, well, we can sort of immediately see that this terminates, because if we give a monomial a weight according to the z, well, this at some point will have no more z's. So if we have something, it will have at least one z or no z's. And well, if there's one z, we cannot rewrite it. And if there's no z, we cannot rewrite it. So this surely terminates, but what about injectivity? So the second essential of rewriting is the notion of confluence. Essentially, let's assume that the map from normal forms to the basic algebra is onto. How could it fail? So let me give you an example above. Let's assume that z squared rewrites to xy. Then what happens with zxy and yxz? Well, because zx squared is x times y, morally xy should commute with z because it's z squared. So this should be 0, and it is. But these two things cannot be rewritten because they have no z squared. So these two monomials, they are both irreducible, but they map to the same class modulo this relation, and that's bad. But well, the obvious thing to do is, oh, well, let's add this relation, because if it follows from this one, let's add it and see what happens. Now I added a bigger set of rules. Now this set will be smaller, and maybe now injectivity will be saved. In this case, it is saved, but if you know a bit about this example, you know that this choice is better because this has no overlappings. Okay, so basically the definition that I want to give now is precisely that the system is confluent is a projection is injective, and it's convergent, meaning that it's confluent to something and it finishes if, well, it happens. Sorry, it's convergent if both things happen. So the main objective that we're looking for is an effective and verifiable criteria for convergence. When is a rewriting system convergence? You give me the datum of x, of w, and of f. I want to look at it, produce finitely many, let's say, monomials or something, look at them and say your system is confluent. Now I will give you a much more complicated answer that reduces to that known criteria later. So let me tell you how to discover this. So if you know what the Diamond Lemma is, great. If you don't know what the Diamond Lemma is, even better, because I want to show you how to discover it without knowing that it exists. So again, what is an effectively verifiable criterion to determine confluence? Well, the first idea that we can think of is the following. What happens if we forget about a rewriting rule? So let's think about the situation where everything rewrites to 0, and I will call that system sigma 0. What happens in this case? Well, in this case, convergence and termination is trivial. Nothing happens. And basically, either something is divisible by a word, and then it's 0, or it's not, and then it survives and it's irreducible. And moreover, sort of this algebra itself is really simple. Either you multiply two things and they are divisible by some w, or not, and then they survive. So multiplication is 0 or none. So this is what are called monomial algebras, and this is what Green, Happel, and Zakaria would call zero relation algebras. And now, because, well, in this case, there is an obvious isomorphism between this and that, and note that that the leading terms of this and the sigma original are the same. So these two things are a priori are the same. So we can rephrase our wish by saying that sigma is convergent precisely when the map that looks at a monomial and sends it to its coset is an isomorphism. And this is tautological, but it introduces some extra structure. This is an algebra. And this is an algebra that is obtained from this one, or we want to obtain it because we want to say that this is an isomorphism by introducing some lower terms. If f is not 0 and we have a partial order, remember that I'm assuming this is terminating, we're sort of introducing lower terms that modify the multiplication table. So probably you're thinking, oh, this is a deformation. This is a deformation of this one. And basically, yes, we're saying that the system is convergent when this is a deformation of this monomial algebra. Now, here we start with the second bit of the talk. Basically, once we start talking about deformations, then, well, we need some better tools, because just checking that isomorphism is not enough. But then we sort of want to take a deformation theoretic point of view. And we know that sort of the general principle that surely has been explained in previous talks. For example, in the talks of Ursi, where he explained how to enlarge a DGAS algebra into something quasi-free. What we want to do is we want to take an algebraic object or a topological space, or, well, I wouldn't dare talk about more complicated objects that I don't know, but we want to take an object and replace it by another object whose homotopy type is the same, but whose behavior in the homotopy category is nice. They're a cofibrant object. So in the case of associative algebras, we can do this, and I'll explain in a minute. But surely this idea hasn't mentioned that we want to replace equality by a witness of equality. We want to say not that two things are the same, but that two things are the same, and that this thing guarantees us that those two things are the same. And so this process naturally leads to homotopy theory. So let me give you an example that has already been explained, because I think this is instructive. The talk of Professor Whitehouse explained multicomplexes, right? And if you tell someone what a multicomplex is, and they already know what a chain complex is, they may be confused. At least when I first heard of them, I was confused. So the algebra of dual numbers is the algebra whose representations are chain complexes. It's just defined by one letter whose square is 0. It's monomial. And what I want to do, as I explained before, is add a witness that says that this is 0. So, okay, d of delta 1 is delta 0 squared. Great. But now I look at the new algebra that these two bits generate, and there's a problem that there's a new spurious cycle, and then I need to add d2 to kill that commutator. Then a problem arises, and now there's a new cycle in degree 2, and I need to add a third to kill that. And you get the idea. It continues, but once, oh, I meant to say continues here, but the pattern continues, and we discover the notion of a multicomplex. So this is just the Kosul resolution of delta. And then this equation is only true up to a coherent sequence of witnesses. This is maybe an example that follows from the Kosul theory. So in some sense, it may be difficult to convince you that what I will explain is helpful here, because the machinery of Kosul, the Kosul theory is wonderful, and we like not to escape it. But well, in this case, what I will explain this cannot sometimes be treated with Kosul theory. So what are the objects that will resolve DG algebras, or associative algebras in general? Well, these are the cofibrant objects in a certain model structure of differential graded algebras. Now, in general, the homotopy theory of algebras over operas is quite complicated. It's one has to do simplicial resolutions, and one has to work with a lot of care. But because the associative algebra, associative opera, which is the one that I'm thinking of, is free as a module over the symmetric group in each degree, we have no we have no characteristic problems, and we can work with DGAs. And here I stress zero characteristic, but you don't need to do that. You can work in any characteristic with associative algebras. In particular, work of Hinich and Jardine shows that, well, the weak equivalences are the quasi-isomorphism, so things don't change there too much. The fibrations are surjections in each degree, and the cofibrant objects are certain Sullivan algebras, right? So this surely were mentioned, or perhaps not yet, but well, the Sullivan algebras are what? Let me tell you what they look like very quickly. They are tensor algebras that are free, where W is graded, so graded, and, or let's say homologically graded, and it also is weight graded. So let me call the homological graded sup and the other up. So this is a weight grading, such that if I take the differential of something in large degree, it falls into the subalgebra generated in smaller degree. So all of them. So there's sort of a triangulation of the algebra that allows you to do arguments of working one cell at a time that would be unavailable if the triangulation is not there. Like there are free algebras that are not cofibrant, so you need to be a wee bit careful. And basically the object that I'm interested in now is simply a surjective, perhaps I meant a cyclic fibration, where this is a Sullivan algebra. Okay, and the idea now is that I will explain to you how to construct this and how to link them to rewriting systems. Okay, but so what is the first step for studying resolutions? The first step was actually let me say, produced or considered by Shafarievich in the 60s, along with Golod, and then Golod himself wrote a paper where he explained how to use a certain Shafarievich complex to begin to build models of algebra. So let me break down exactly what this object is. So we have the following situation. Remember that our general setup is that we have an algebra. We have certain relations or a certain ideal of relations that we want to kill. And what this Shafarievich complex is doing is it's adding to A some generators that are in bijection with S, but they're moved 1 degree up. So we're adding S 1 degree up. So this is a copy of it. And we are using those new objects to kill the elements of A. So essentially what this construction does, it's similar to the Kosul complex in commutative algebras, where you do a tensor symmetric algebra of a copy of V, and this ends up being the exterior algebra because you shifted it, but in the non-commutative setting. So it's slightly more complicated from one point of view, slightly less complicated from the other, but it has the effect that it's zeroth homology if we choose the parameters correctly. So if we choose A to be the free tensor algebra, if we choose S to be the set of words that we obtain, so the graph of the zero rewriting system, then the resulting complex First, it is a Sullivan algebra because the differential of this sort of lowers the, if you want, the grading given by the monoid itself. And second, its zeroth homology is precisely what we want. It kills the word the words that we want, but something may pop up in degree 1 or 2. We'll see about that. So our anchor to state this effective way of checking for convergence is the Shafarevich complex of the monomial algebra associated to rewriting system. And what we do is we sort of want to take this as the 0 and 1 step, and the 2, 3, and 4, we leave it in some resolution. So from now on, in my head, I will fix a resolution that coincides with the Shafarevich complex in degree 0s and 1, and I have fixed it to be acyclic, and so that it becomes a resolution of my monomial algebra. And in what I mentioned before is that I want it to be graded by the monoid, meaning that, well, if you think about the Shafarevich complex, well, it is the tensor algebra. The tensor algebra is graded by this monoid. I'm adding a copy of words, so those words are graded by the monoid, and I want to keep that. I want everything to be graded by the underlying monoid. So actually, perhaps my organization there was a bit misleading. I may be able to tell you now exactly what our first result is. It basically we proved that the following happens. So let me perhaps break this down. We have this Shafarevich complex, and now we take a resolution, and this gives us a resolution of this monomial algebra. And what we have shown is that if we can take this resolution and perturb it, I'll explain that in a minute, but if we can perturb it, we can deform it into a resolution of a sigma, then the system is confluent. So confluence happens precisely when any cofibrant resolution lives quite close to the starting resolution in a precise sense that I'll make later. Very well. So what happens in this situation? The theorem that we prove is that the system is convergent if and only if any acyclic extension of the Shafarevich complex of the associated monomial algebra admits a perturbation which is compatible with the system and which is an acyclic extension of the other Shafarevich complex. So perhaps if I make a little diagram, we start with a sigma 0. We are aiming to say something about a sigma. We take the Shafarevich complex, we extend it, so this contains now some really nice resolution. This is a resolution, and what we have shown is that we can deform this into another one, so a lower order term, and obtain a resolution of this which actually extends the other Shafarevich complex if and only if the system is confluent. Now, what do I mean when I say sigma compatible? This is perhaps not too technical, but I just mean that the perturbation here, well, it lowers the weight grading that we chose at first, okay? And also that, well, being sigma compatible perhaps also means that it extends the Shafarevich complex. I'll state it perhaps clearly later, but let me clear this. And let me perhaps, yes, spell this out for a second, because those who know what the Murray-Cartan equation are, and perhaps now everybody does because it was presented, will understand that, well, what's a perturbation? It just means that I took my original differential d, I added a term to it, and it squares to 0. Now, of course, d itself squares to 0. So we get this equation, which, well, you can write into a Murray-Cartan equation, I will explain before. And the compatibility means that, well, it's creating the correct lower term. So if I restrict this to degree 1, where we are living in the Shafarevich complex, then this perturbation must add the correct lower terms. Because, of course, if we don't add the correct lower term, we have no hope of obtaining an acyclic extension of the Shafarevich complex and a model of the new algebra. Okay, now the question is, yes, perturbation theory is really nice. It can be used to prove wonderful things, and but the problem is that sometimes the input of a perturbation theory method is an isomorphism between two objects, one who has a structure and one who doesn't. So it's perhaps begs the question, but well, how do we check that we are in a perturbation theoretic setting? So the idea is that perturbation theory also comes with an obstruction theory to perturbations, meaning that if one wants to perturb something, there are obstructions to it, and that is written in the lovely language of DG Lie algebras. Now, perhaps I don't want to jump into that just yet. Perhaps I do want to say that, well, I think L-infinity algebras have been mentioned already. But yeah, I'll just talk about good old DG Lie algebras. So let me explain why exactly DG Lie algebras appear when we are taking an algebra, producing a cofibrin replacement, and trying to consider perturbations of that sort of homotopy type. So there's such a thing called a tangent complex that is associated to every resolution of an algebra, or perhaps an object. I mean, I'm using the word tangent complex to mean the DG Lie algebra of derivations of a resolution, but some other people use it in a different sense, in a more geometrical perhaps sense. But basically the reason why we like this very much is that there was a lot of mottos and insight developed by Deligny, Drinfeld, and Fagan that were formalized by Jacob Lurie and Bridham more or less simultaneously, that say that DG Lie algebras control any sort of deformation problem. Now, I think I was watching a video of a lecture of Lurie some days ago, and he used the word prototheorem to refer to this, which I thought was really nice. So basically, whenever we have a deformation problem, such as what I described, I have some object I want to deform it, there should be a DG Lie algebra that tells me you can, you cannot, here's the equation, here's the obstruction, and so forth. And well, here, for example, equivalence between categories of, well, these are probably infinity categories. I don't want to state a precise theorem, so probably this should be a prototheorem. But yes, there should be a DG Lie algebra that tells us and dictates how our perturbation problem should go about. So let me explain to you what that DG Lie algebra is, and perhaps get into more precise statements regarding perturbations. So what I want to do is I want to explain to you not only how to find an effective criterion to check for confluence or convergence, I must say, but rather that each cofibrin replacement of an algebra, sorry, I was looking at the chat and got distracted. Sorry, each resolution of the algebra gives its own criterion. And I think Jim has said the philosophy leading to that prototheorem has much older ancestry. Okay, yes, I may not, I don't want to assign, I don't want to assign priority. I just know that those three people definitely say there's something, but I would be happy to know the complete history.
They deserve credit for a proof as opposed to hand waving.
Okay, very well. And now what I want to say is that whenever we have a model, so we have taken some free algebra and put a differential. Well, what's a perturbation is just choosing another derivation so that if I add it to D, it still squares to 0. So I'm sort of infinitesimally perturbing D, but it still squares to 0, gives me an algebra. And if you have seen this equation a few times, you can rewrite it in the famous Murray-Cartan equation. where this new differential is just the adjoint action of the original differential. And this is an equation in a DGAS algebra, in the DGAS algebra of derivations of this model. So as I was saying, this is the Murray-Cartan equation. And what I want to do is now focus on, again, on the Shafarevich complex. So I will write the DGAS algebra of derivations of any model extending the Shafarevich complex by G sigma 0. And then basically what I'm looking for is a Murray-Cartan element in that DGAS algebra. Now, let me explain precisely that theorem 1 implies that the following happens. So let me be very systematic here. First, if I restrict f to degree 1, then this coincides well with the linear extension of our rewriting rule. It's adding the correct lower term. So I had d killed w, and I need to add minus f of w to actually kill the new relations. The second condition is that, well, because our rewriting system was assumed to be terminating, this has to lower, or could be modified a priori to lower the some partial order, but the conditions of the theorem also state that in degree 2, it should lower also the partial order that we have obtained, or the weight grading. And finally, a particular consequence of that theorem is that this f satisfies the Murray-Cartan equation in degree 2 because it is a perturbation. Now, the Murray-Cartan equation is an equation that lowers degree by 2. So in degree 1 and 0, there's nothing to say. It holds trivially. So the first situation where something non-trivial could happen is in degree 2. But the second result that we have proven is that this is enough, basically. If we have sort of, I mean, this is just a mnemonic, but if we are okay with the sort of original datum, if we perturb the relations in the right direction, and if the Murray-Cartan equation holds in degree 2, then we're good. We can deform the whole algebra to a bona fide sort of Murray-Cartan element. So let me sort of state this precisely. The second theorem, which is perhaps the effective part of the whole story, is that the system is convergent if and only if we can find an element which is not at Murray-Cartan a priori, it's just an element of the Lie algebra, which perhaps I should have written has degree -1, with those 3 properties. And the proof is inductive, sort of. It's similar to the computations that people doing rational homotopy theory would have done. You know, you have a grading, it lowers the weight degree, you have a cycle, you want to prove that it's a boundary, it's in the image, and then, you know, you pull your sleeves up and you obtain it. So if those 3 little conditions hold, then we can obtain a perturbation, and by our first theorem, then the system is confluent. But it would be good to spell out exactly, it would be good, and let me go up for a second, it would be good to spell out exactly what happens in degree 2. Now we have reduced things to finitely many information, 0, 1, and 2. So what happens in degree 2? So let me, again, revisit the Diamond Lemma from this perspective of these 2 results. And here we will sort of bump into, without trying, we'll bump into the essential notion of the Diamond Lemma, which is what's called an overlapping ambiguity or an obstruction. So let us go back to the original Shafarevich complex, which is the one that is used to resolve our monomial algebra, and pick some acyclic extension. Now we know, but by the third condition of the theorem above, that we need to look at elements in degree 2. Now, an element in degree 2, when I take its boundaries in degree 1, and then it belongs to this subspace, basically because it has to contain just one word of homological degree 1, and then we can decorate it and pad it with any word in degree 0. So it looks like U, tensor, a word that we started with. Remember that V1 is just the linear span of a copy of W. and something else. And I will define, and I will explain immediately why this is important. This element is called the obstruction associated to this degree 2 element. So what I'm doing is I'm applying f, thinking that w is now a word. I get an element in the tensor algebra and I can take the product, and I get an element in the tensor algebra. So I'm getting just a polynomial in the tv0 is t of x, right? Remember that v0 is t of x. So the sort of final, I suppose, theorem is the following, that these obstructions that are built from a specific model in degree 2 are precisely the elements that dictate if there is confluence or not, or convergence or not. So basically what we proved, which is the sort of coordinate independent Diamond lemma, is that this rewriting system is convergent if and only if, whenever I pick an homogeneous element in degree 2, this obstruction can be rewritten to 0 using a sequence of reductions from sigma. Now, if you know what the Diamond lemma states, this will sound very familiar. If you don't, what this is saying is that once I have built the model, I can produce the obstructions. In general, this space will be finite dimensional in each homogeneous degree. And I can look at this as a polynomial in t of x. I have my rewriting rules, and if I can rewrite it to 0, then things are fine. And if not, we're in trouble. And that's it. This is the effective criterion that we have rediscovered, if you will, because of course the Diamond lemma exists since '85, and previous work by other authors has also also suggested Diamond lemmas not for associative algebras, but in other situations, such as, for example, the Buchberger criterion in commutative algebras, right? So what's the idea of the proof? I mean, I have the bad habit of saying that the proofs of the in the talks that I give are simple. I don't know if that helps, but basically, what does the Marquardt equation say? Well, it says that f with d plus d with f and f is 0. So this element, fdc, is precisely minus sc. Why? Because, well, f has to coincide with minus f in degree 0, or in degree 0, I suppose. And that means that if we write this f of c, again, it's this c was of degree 2, f is of degree 1, so this is of degree 1. We write it like this, then this remaining summand, this bit here, is simply a linear combination. An element in the ideal generated by our graph. And what this Marquardt equation is very, very concretely saying is that this obstruction has to be written in terms of basic reductions. And conversely, sort of this went from one direction to the other, but sort of conversely, if we can write things in terms of the ideal, this immediately suggests how to modify f so that this equation holds. So the Marquardt equation holds in degree 2 precisely when we can find a witness that each obstruction can be rewritten to 0. So the Marquardt equation in this very, very precise context is giving us witnesses that our system is convergent. Now, I believe I have like 17 minutes left or something like that. So let me explain to you how to recover the usual Diamond lemma. I haven't stated it, but basically by explaining to you how to recover it, I will obtain a statement of the Diamond lemma, right? So at this point, I wanted to switch to my other board. I'm sorry I didn't use it before. I hope you can you see it? Yeah. So what I want to explain to you is how to recover the usual Diamond lemma. And the idea is that whenever we have a monomial algebra, so I'll keep with the notation as before, this is t of x W, there's a very, I find it pretty, resolution of this monomial algebra by what's called the inclusion-exclusion, let's say, algebra. So the idea is as follows. I'll think of this algebra as, or perhaps of each element of T of X. Each element of T of X is just the linear span of this. So it's an homogeneous element here. And then that element, well, it could happen that it's divisible by an element of W and then it vanishes, or not. And basically what I want to do is sort of coherently exhibit this as something where all of the elements U vanish when they're divisible by elements of W. But the problem is that I don't want to choose one occurrence of W. I want to choose any of them. So what I will do is to each U, I will assign, I don't know, I think I decided a good name for it is the deck of U, even though actually this construction is due to Datsunko and Anton Horeshkin, where yeah, they actually do it in a more general setting, but the deck of U will be in bijection with all the occurrences of divisors. Let me just write it like this, but this is just in bijection with all the instances of divisors of words that divide U. So let me make a drawing. What I'm saying is that I'm taking U, which is some monomial, and I'm choosing a symbol for each time I can find a W in here, okay? And then to each deck, let me see if I can make a coherent picture. To each deck, I will assign just the Grassmann algebra on that deck. So I have wedges of this, and I like to think of that as sort of ways of saying that sometimes these words can be, well, this should be a wedge of what, 1, 2, 3, 4, 5 elements. So this consists of schemes where I'm marking multiple occurrences of W. Okay. Now, what I will do is I will take the tensor, I will take the sum of all of these. So let me do that this was step number 1. This was step number 2. As a step number 3, I will take the sum of all of these Grassmann algebras. So, and actually, let me say it this way. I'll take the sum of a copy of U, tensor all these Grassmann algebras. Okay. So what I'm doing is I'm taking the tensor algebra, and each monomial I'm enlarging it by some vector space. But the point, so this is U in this, is that I can make this into a DG algebra as follows. The differential will simply erase one instance of a divisor at a time. So D of DUI, let's say J is sort of the Kronecker delta. And this is locally in each Grassmann algebra. And then I extend this multiplicatively with the Leibniz rule. Now, something that could be confusing at this moment is that this does not look like a free algebra because these are Grassmann algebras. But note that I have not defined the multiplication yet. These are Grassmann algebras that I like as vector spaces, but I haven't defined them. I haven't defined the algebra structure. And the algebra structure is kind of simple enough to define. I just will concatenate the schemes one next to the other, and they respect this grading that I put to the left, because if I concatenate U and U prime here, well, I'll get a picture that will correspond to U times U prime. So this thing is X graded. You can check that in degree 0, it is the, and degree 1, it is the Shafarevich complex, because what we're doing is, I'll explain it in a second, I'll explain to you how it's the Shafarevich complex, but it is X graded and it is a resolution. Why is it a resolution? It's easy to see it. It's one of the wonderful things about this resolution is that it's easy to see as a resolution. So the deck of U, it could be empty or not. If it is empty, well, I haven't put anything new. I just put a one-dimensional vector space here, and I'm just keeping the monomial that I want to keep. If it's not empty, then if the number, so sort of if the size of the deck of U is equal to L, then this thing is just the singular complex of the L-1 simplex. I'm just removing, right? So in a very precise sense, I put a contractible space of choices that make this, that witness that this U was divisible, but I didn't make a choice. I put the canonical contractible space of choices. So this is a model of that. And what happens what are its generators? So what is it generated by? Let us think about that for a second. Well, essentially, by how I have defined this, if it's going to be free, it's going to be free over the indecomposables. And essentially, you can convince yourselves that sort of a divisor scheme is indecomposable precisely first when the divisors occupy all of the space, because if not, this I can consider it an empty divisor scheme and concatenate it out. And second, when either things overlap like this, or when we have perhaps a word that is going to be 0 and something inside. So we either have type 1, which are overlappings, or type 2, which are inclusions of divisions. Now, again, if you know what the Diamond Lemma is, this should ring a bell because there's overlappings and there's inclusions. And now, finally, let me think about what happens in dimension 2. So in dimension 2, irreducible degree 2 elements are either overlappings like this, or an inclusion ambiguity like this. And what happens when I take the boundary of this? Because remember that to compute obstructions, I have to take the boundary, see what gives, and apply the potential Mayer-Cartan element, or actually whatever writing system. So let's say in this case that this corresponds to W, and the remainder I will call it A. And let's say that the other blob corresponds to W prime, and the bit that remains here, I call it B. Then if I take the boundary of this element, what I will get, let's call that C. If I get the boundary of that element, what I will get is the following. Well, first, let's say we remove this one. So once I remove this one, I will have a bit that corresponds to B, plus the bit that corresponds to, so B was this bit, that to W prime. And in this algebra, this corresponds to the degree 1 element copy of W, that I will write it like this. And this here corresponds to concatenation. So this is just, let's say, B tensor 1 times 1 tensor EW. I'm sort of, sorry, I mean to say W prime tensor EW. And someone that doesn't want to be so precise will just write it like this. And what happens to the right? Well, it's similar. I would draw a similar picture, and what we will get is 1 tensor A times W tensor EW. So this is A, sorry, the A should be on the other side, of course. Let me quickly fix that. So this will be W times EW times A tensor 1. And again, someone that knows what this looks like would write it like this. And if I apply F to it, so if I compute the obstruction, what I will get is B F of W prime minus FW A. And this is the S polynomial. So I chose a resolution that suggests itself quite not immediately, but it suggests itself, and it gives you exactly the definition of an S polynomial. If you do it for this one, you will get the S polynomial for what's called an inclusion overlapping. But basically, let me give you the example that we had before, where we had Z squared and we rewrote it to XY, right? And I told you that there was an issue with zxy minus xyz, and the reason that appeared is because I performed this sort of quote unquote trick on the fact that z cubed has two instances of z square in it that overlap at z. And if I consider this as an element of degree 2 in this model, and if I compute S of C, I will get precisely this element, which I checked it didn't rewrite. So my choice of rewriting system there was wrong, but well, it helps to explain the method. And so what this means, and let me see if I can actually state the Diamond Lemma as a corollary of this explanation. It states, so as a quote unquote corollary, the Diamond Lemma, the classical, let's say classical Diamond Lemma, that a rewriting system sigma is convergent if and only if all, what do I want to call them, S polynomials can be rewritten to 0, if and only if all S polynomials can be rewritten, to something, I suppose something doesn't sound as technical, but something smaller. And what I mean, the first condition is clear from I suppose what I just explained, but the second condition also follows from the first or the second theorem that I stated, because it says that it suffices not for the Marquardt equation to hold on the nose, but that it lowers the degree. So a more sort of the way that usually sometimes we can show that the diamond condition holds is just checking that we can find an order so that our S polynomials are smaller than what we began with, okay? Which is, we don't even actually need to produce a witness that they are 0, but we can just show that we can sort of shove them under the rug. Very well. So I think we started a bit later. So are there 8 minutes more, 10 minutes more? So... Oh, I can't hear you. I'm not sure why.
Take you 10 minutes.
Okay. So let me see if I can go back to the slides. And so here was all the explanation, and now there's an improvement, let's say, because sometimes if your set of words and if your alphabet is large, then of course those simplices might be quite large. Their dimension may be large, and then it's not great to have to check all those S polynomials and all those inclusions and all those overlappings. So there's something called the triangle lemma. Now, the triangle lemma essentially tells you first, and this is stated, for example, in Bergman's paper, that you can forget about inclusions. So sometimes if a word sits inside the other word, well, technically you can remove the bigger word because it follows that the bigger word and the smaller word, it follows that the bigger word is implied by the smaller word. Now, in the monomial case, this is obvious. In the case that there are lower order terms, this is a bit more tricky, but it's true. And second, sometimes it may happen that one overlapping implies the other. What do I mean by this? Let me give you again an example. So let me see. Consider the following situation. Where is the draw? So let's consider the situation that we have one variable as before, right? But now we don't require that delta squares to 0. Let's say that it's 4th power 0. Or actually, no, I don't think we don't even need to do the high. Its 3rd power is 0. So this is a non-Kosul algebra, and I want to find the minimal model of it, and I'm not sure how to do it well. What this says is that we need to look at words, so many deltas, and we need to start looking at occurrences of delta cubed inside it. Now, as I said before, if we want to obtain the composable elements, we need to start at the beginning. So here I marked d cubed. And then, well, I can mark d cubed like this. But this is also an overlapping. So here in this situation, it seems that a priori we have to check this. And we have to check, well, that. And now what we observe, and this is sort of the improvement, the optimization to the algorithm, is that if we erase this, and well, necessarily erase that, we can actually produce a new scheme, a new overlapping. And so in some sense, this was not optimal. There was some superfluous information, and sort of d5th is 0 because d4th is 0. So we're removing superfluous information. And the idea of the triangle lemma is to state that a bit more precisely. So in this case, the triangle lemma is implied by the resolution I found and that Chuang and King found independently in unpublished work, where we use, again, we will use sort of overlappings, but they will be produced in a more delicate way. And sadly, I cannot give you a nice interpretation in terms of polytopes. And I would very much like to know if the model that I found here, if you've heard about it, can be stated in terms of polytopes or something like taking the simplices and cutting them. I don't know. It would be nice if whenever someone gives you a word that is actually a basis here, you can produce a polytope that creates the correct differentials in the model that I found. I don't know how to do that. So let me explain the model quickly and explain to you how it leads to the triangle lemma. So let us try to make things a bit more optimal here. So again, we begin with a monomial algebra like this with some words. And what we will do is also consider schemes of divisors. But the first thing that we will do is we will sort of build them inductively. And they are built inductively because this allows to remove any extra information. So I will tell you inductively how to write this divisor schemes. So first, we will declare that, well, if I take a single letter in the alphabet, I get, well, an empty divisor scheme. Second, I will declare that if I take one of the words and I circle it, making it now of homological degree 1, that will be an admissible, let's say, divisor scheme. And inductively, this are what are called zero schemes. Actually, they are called zero chains. These are called one chains. And inductively, let's say that I have built an n-1 chain. So there are n-1 bubbles. Then I will say that I have created an n chain if I can append a relation here with the following properties. That first, first I'm appending a relation, but second, if I remove any tail of it, if I remove any word at the end, I cannot do it again. So basically, it's saying that I can append a relation at the end, and that process is not implied by a smaller word that I could have created. Now, I have been imprecise, and if you know what the definition of an Ig chain is, perhaps perhaps this is a bit too hand wavy, but that's the idea, that we are creating these divisor schemes, but in a much more controlled fashion. We're not just letting everything go through the floodgates. So once we have constructed them, we will take the free algebra over them. Basically, the way I have constructed them makes them indecomposable for the interpretation here. So those will be our generators. And so we'll take the free algebra over those chains of relations. and I will define a differential. And now the problem, or the difficulty here, does not lie in finding the decomposables, but rather in finding the differential. And the way you find that differential is if you have a scheme or a divisor scheme like this, you need to find every way of decomposing it into schemes you need to find every way of taking your monomial, breaking it into bits, and producing in each bit a decomposition scheme. So this is a bit more complicated. It does not follow by removing bubbles, but rather keeping the bubbles and reorganizing the structure so that we still have schemes. So if there are T bubbles here, total number of bubbles here has to be T minus 1. And just to give you an example, because I know I'm being incredibly imprecise here, if I look at the example that we had before, where we have T cubed, and I have circled all of them, then the only way I can write this with 0 bubbles is T tensor T tensor T. And if you know a bit about A infinity algebras, you'll know that this is an M3. And you know, if I would have done it with T tensor T tensor T tensor T, and I have this and that, well, the only way I can sort of scramble this into 2 bubbles is like this: tensor T plus T tensor T T T and a bubble. And well, this again, it's harder to describe the differential, and that's the whole complexity of the paper, but it can be done. And again, if we compute the obstructions, this creates the S polynomials of sort of minimal overlappings. And I mean that both the situation is appropriate because this is the minimal model of any monomial algebra, and that's one of the reasons that we were interested in obtaining it. And of course, sorry, and of course, this being the minimal model means that this is the optimal. So the optimal criterion is this one, in the sense that if I have fixed an alphabet and if I have fixed a set of words, this is the least you'll have to do. Now, perhaps someone found a better presentation with X and another set of W. Perhaps that leads to less overlappings. That could happen. But every time you fix X and you fix W, this is, from a strict point of view of labor that has to be done, the least that you must do, because this is the minimal model. Okay, so going back to the slides, perhaps I want to start finishing the talk with a motto of Kontsevich and Soilman that write in one of their papers that the deformation theory of associative algebras is sort of a guide to developing other deformation theories, and sort of as a converse, if you think about a concept coming or deserving to be, you know, the deformation theory of everything, as they say, well, you should test it for associative algebras first, because that is kind of a good kind of testing ground for that. So I think that what I have explained and what we have done with Vladimir is sort of a good example of this, meaning that you know, we reframed the Diamond Lemma in terms of homotopical methods and the tangent complexes and Murray-Cartan equations. And even though perhaps if you look at the paper and you look at the computations, they're not so difficult, the good thing is that they explain how to do it for operads, for example. And in the case of operads, for example, we don't know how to build minimal resolutions, but perhaps this justifies taking the trouble of doing that. And when I'm sorry, when I mean we don't know how to build minimal resolutions, of course, there's a lot of methods to doing. What I mean is we don't have a description in the sense I give you a presentation of a monomial operad by monomial relations. You define for me combinatorially a set of unique chains and a differential, and that's the minimal model. I'm not making a statement about what other people have done. I'm making a statement of what I could not do. So for example, the inclusion and exclusion model of Datsynkon-Khoroshkin works for operands, meaning this divisor schemes, I can draw them on lines, which define sort of unary operations, which define associative algebras, but I can draw them on decorated unary operations that define shuffle algebras or twisted algebras. I can draw divisor schemes in trees, which define non-symmetric operands. I can draw divisor schemes in shuffle trees, which define shuffle operands. And so their method of adding simplices to kill relations works in general in sort of in a situation where you have a colored operand that is set theoretical. And in fact, if you look at the situation for operands, but I think I didn't want to draw those things there, you recover the Diamond Lemma that is proven in the book of Moira Bremner and Vladimir Datsenko of the sort of Diamond Lemma for shuffle operands. What would be interesting is to understand how to perhaps use models to obtain better optimizations of this, because, well, in particular for operands, I think that if you ever tried or successfully computed like Grosvenor bases and things like that, it's definitely a lot of work to look at all overlappings, and it would be great if someone can figure out how to optimize that. I mean, even for operands that are monomial and are easy, you need to look at so many overlappings that now I think I'll finish here, but I want to make one more comment, which is the following, and perhaps I think I may have said this I may have given this example to people before, but even if you look at the following operand, if I take a non-symmetric operand and I kill all trees of weight, sort of all trees of the same weight as this, so of weight 3, we don't know what the minimal model of this is. And one of the striking features of this is that if you look at its bar complex, and this is an example by Emil Skolberg it's sort of unpublished computations, I suppose. If you look at this tree, well, this tree has many instances of trees of weight 3. For example, this will be a divisor, and it has this and this. This would be a divisor, and this would be a divisor, and this would be a divisor. So it has many instances of that. But if you compute the homology of the bar complex, which is graded by trees, so it consists of trees, this bar complex has homology of dimension 2 in degrees, and I know the representatives, so let me draw them. One of them is this. That's one representative, and the other representative is, let me finish like this, and the other representative is this. No, that's too many. Do I have 1, 2, 3? So if I start here, right? Sorry, there are too many bubbles there. Let me rewrite it. What I mean to say is this and this. So this is 1, 2, 3, 4. So degree 4, and then this. That's 1, 2, 3, degree 5. And if you know what happens in the algebra case, if you look at bar complexes and look at the graded components, these things are pure of dimension 1. Whereas in the case of operands, even for this situation, there's some homology in 2 different degrees, and that ruins some arguments. So for example, this suggests a definition of minimal overlappings, but the fact that even one tree has 2 different minimal overlapping schemes is already telling us that, well, something much more combinatorially rich is happening, I suppose. Okay, so now I think I will finish. I think it's time to finish. And yeah, thank you for your attention.
Gràcies per la teva xerrada. Thank you very much for your very nice talk. And we are going to compute a lot of examples if we can.
Thanks. That would be great.
Yeah, that's very tempting. That's very tempting. Are there any questions? I think that there was, right, a question of him again.
Yeah, what I meant is
you can-
K-linear. Oh, sorry. Yes, go ahead.
No, well, I mean, can you read it or?
Yeah, it said colored operas are expansive colored operas. What I mean to say, if I wasn't precise enough, is K-linear operas that are obtained by linearizing set colored operas. So commutative operad, for example, but not the Lie operad, right? Like if we want to apply this method for the Lie operad, we need to embed a Lie algebra in an associative algebra via PBW, and that's when Grobner-Kirchhoff basis for Lie algebras work.
Okay.
And sorry, I see that Isaac Wren is in the audience, and there's a paper of him and Leib Malbos where they explain how to use polygraphs to resolve operads. I cannot say anything significant, but I think that's also a paper where this problem is potentially addressed in a different language, which, well, I hope I could become acquainted soon.
Okay, so are there any more questions?
Yes, perhaps a small question.
Go ahead.
Is there a relationship with the work of Squire and Kobayashi?
When you mean so, I think when I learned about writing theory, I started with Buchberger and then with Bergman and Grobner, and maybe I never actually read in detail the works of Squire. Perhaps could you tell me just quickly?
I think that the essential difference is that Squire starts precisely from what you explained, the rewriting system, but then he does not make the simplifying assumption that somehow you can reduce your reductions to reductions of monomials, but you have really general reduction rules where you can also reduce a word to another word. And but then what is very interesting is that there are resolutions which are constructed for these general rewriting systems, and there the really important notion is the notion of a critical pair. And this is very much resembling to what you call these overlapping monomials. It's the same thing. Just instead of taking monomials, you take reduction rules.
Yeah, I mean,
and so it would be very interesting to actually generalize your method to this general to classical rewriting systems.
Right. I mean, I think that one of the first times I heard about the work of Squire was when I was reading about polygraphs, and again, I think that that's something that I need to read more about. Perhaps the idea of that I sort of the idea of producing the witnesses of relations is precisely hidden in the idea of polygraphs. I cannot tell you precisely how the work of Squire is recovered, but I remember that Vladimir may have mentioned it, and we have definitely cited it in our paper. I'm sorry I cannot give you a more precise answer.
Thanks. Anyway.
Are there more questions?
I have one if nobody else has anything more important to ask.
Okay, so go ahead.
Can you just give me some intuition? So usually when I hear that an operator is going to lower the degree. So you had operators lowering the degree. You had X as your grading. So you want to lower the X grading. Now, usually I think of that as just something to make sure, just a technical condition to make sure that some infinite sum is going to converge when you use the transfer. But you're not doing that, are you? You're doing something different. What can you give me some intuition about what?
I mean, in some way, we are doing that, right? Because the point, so the idea is as follows. You have your monoid, and then when you choose a multiplicative compatible Noetherian partial order on it, it helps you, well, it actually gives meaning to the statement, the weight goes down, right?
Yeah.
Because a priori this is weight graded, but there's no order. So once you choose an order, and in general, what happens is that not only you have a partial order, you have a total order. So you have, you're in the Grosvenor basis area. So so yeah, basically that ensures that the whole perturbation machinery goes through.
Okay.
I mean, if not, I remember that when I was back in Buenos Aires, like a while ago, my master's advisor was working with a student of his to do a topological Diamond Lemma, where they were considering topological algebras, and they were stating things in terms of, if you can rewrite something so that epsilon is smaller than this, but maybe you can just do it for complete algebras. It's just that you won't have like I'm not sure what the statement is there.
Okay, thanks.
So, are there any more questions? So, if there are no more questions, let us thank Pedro again, and also well for the talks this afternoon, well, this evening already here, and let's see let us see you again tomorrow at 12:15 in Barcelona. Thank you very much.
All right.
Pues muchas gracias.